Thank you. Glad everybody kind of stuck around for the end. I'm glad to get to be here to present. The idea of historical preservation is very interesting to me. I have a background in carpentry and woodworking, and specifically in arts and crafts era homes. So, kind of having seen what's happened to these types of this type of architecture over the years, we never really realize how important something is until it's gone and there's no documentation of it. So with that, I'll go ahead and sort of describe the purpose of my presentation, which is to provide a more practical understanding of the methods and approach for documenting using UAVs. We try to kind of get away from the D word just because it's become so ambiguous. But unmanned aerial vehicles is sort of the terminology we use now. Aerotestra, as she said, I started in 2012. Our goal is to manufacture commercial grade unmanned aircraft systems. We do kind of believe that the FAA, as Brandon described, they do see these as aircraft systems, and because of the law of gravity, they essentially have the same impact. So moving forward, we are building systems that will be FAA airworthy approved and follow really in the same rule base that manned aircraft systems do, and that's maintenance, that's airworthiness certification, everything that defines an aircraft that's in the air today. We also offer comprehensive training. So again, as Brandon mentioned, the FAA Part 107 certification only provides you that standard rule base for how and when you're allowed to operate the vehicle. We provide training on the unmanned systems, essentially the robotic interface for how to operate unmanned systems, as well as application-specific data acquisition, data analysis, and visualization. So for what we'll see here, we do aerial photogrammetry, which is stitching together photographs into a 3D topographic model. We would show how to capture those images in the proper way and how to process those images into a 3D topographic map for that application specific. For this presentation, I'm going to provide a definition of what unmanned systems are. Drones has come to mean, again, everything from the little thing that can sit in the palm of your hand to essentially something the size of a 747 that can fly for days on end over theaters of war. And so calling all of those things drones really makes it difficult for us to understand and kind of comprehend what they are. So I'll describe for you what small unmanned aircraft systems are for the most part. We'll look at kind of the two major types of unmanned aircraft, those being fixed wing, which you're normally seeing out there, and multi-rotor concepts, which are like the drones that Brandon primarily showed in his slide presentation. We'll look at some of the processes for aerial mapping and provide some case studies that show how we use that technology. And that's basically taking pictures from the air and then stitching those pictures together into a 3D topographic map with a very high degree of accuracy and resolution, which certainly are different concepts, but they kind of have some relationship as well. And then the methods for providing that geographic accuracy to a model. So even though we can have very small or granular resolution to what we're capturing, how do we provide the spatial accuracy that was described in the LiDAR presentation relative to precise GPS coordinates or actual spatial accuracy. So we have two basic types of unmanned aircraft. Again, I said the fixed wing. We know these as airplanes. They utilize stationary wings as opposed to rotary wings. So they utilize stationary wings, and lift is generated by the air that flows over the wing, and control of the vehicle or steering of the vehicle, which is done by the autopilot system, is by control surfaces, the ailerons and the rudders, that basically deflect air and allow the airplane to steer through the air. The other concept is a multirotor, or VTOL, they're sometimes called. These include helicopters, multirotors, the ones with multiple propellers, and then hybrids, which are sort of a mix between the fixed wing and the multirotor, and they're starting to be introduced. The multirotors generally have at least 2 propellers, but up to 8 typically. They move about a center axis. They orient in space using the relationship between the motor speeds. So to move forward, instead of pitching the elevator down, they speed up their rear propellers. To move to the right, same type of concept. To move to the left, they speed up their right propellers. Or to move to the right, they speed up their left propellers. And so this is how they control their movement or their navigation through space. And again, this is controlled at a very fast rate through the computer's navigation system. This is an advantage. This is an example of a fixed wing aircraft. For an aircraft like this, we want to look at what are the advantages and disadvantages of these two types of aircraft, because they definitely have different use cases. So for a fixed wing aircraft, the flight time is typically much longer, because simply by flying through the air, lift is generated. So it consumes a lot less power than its multi-rotor counterpart. This means that the coverage area for a map that would be generated can be much larger. So you go from 150 acres maximum with a multi-rotor typically, to up to a couple, well, at least 1,000, maybe 1,500 acres, and even more given some fixed wing designs that are utilizing solar power that can fly for essentially as long as there's sun out. The efficiency of solar panels have gotten to that point where they can essentially propel an airplane, but unfortunately not a multi-rotor. So they still suffer from shorter flight times. Easier power loss recovery, so they are safer. If an airplane suddenly loses power, it can still typically glide safely to the ground, maybe not under the best control, but it's not falling out of the pound or out of the sky like a 10-pound brick, which is typically the case if a multi-rotor loses power. Disadvantages of a fixed wing is that they do need a takeoff and a landing runway, so you don't always have that available. They require a pilot with more experience, because the standard for a multi-rotor is typically stabilized flight. So it wants to kind of sit in one place and you can steer it around. For an airplane, since it's moving, you're still essentially flying it like an airplane. So you need somebody who's had experience with flying a remotely piloted airplane. Just generally, because of the rules of how these two systems operate, you typically have to fly at a higher altitude because you have much less time to avoid obstacles. You can't really stop on a dime like a multi-rotor can. So that's going to impact your map resolution. There are a number of other sort of drawbacks related to that, but that's the general idea there. So for a multi-rotor or VTOL, this is most often what is used. Given the current FAA guidelines that you need to maintain line of sight for the vehicle that we manufacture, which this is a representation of, we can get from 20 to 30 minutes. So at even at a minimum height of about 50 meters, where we have very good ground resolution, by the time we cover 30 minutes, we can barely maintain a visual line of sight with the vehicle. So flying for much longer than that doesn't really matter. So until we can fly beyond visual line of sight and do these very large scale operations, multirotors will and are the most adopted means of generating maps and doing most types of remote sensing. The advantages of a multirotor are that they can take off essentially in an area not much larger than the vehicle itself, because it takes off directly straight up and lands in the same fashion. Manual control requires much less experience. You've seen you can buy these at Fry's and the mall and everywhere else, and it is essentially the vehicle wants to try to maintain a very stable position without regard to wind and external forces like that. So, as long as you have some experience with it and you can translate your desire to the vehicle through the controller reasonably well, then you can keep it in the air, as long as you're paying attention. Altitude and speed. It can typically fly at a lower altitude, like between buildings, because you can control it in a much more precise manner. Flying an airplane between buildings, you just generally understand the difficulty that would exist with that. The speed can be much slower because it can go, these vehicles will do from 45 miles an hour ground speed down to 0. So they will come to a hover and can generally maintain a pretty consistent speed over a relatively large area, given the different types of sensor input that's coming to the vehicle. So it's taking GPS, accelerometer, compass data, and fusing that to basically create a position estimate that allows it to fly quite accurately at any speed and in relatively confined locations. As I mentioned, the disadvantage being that it will only fly typically from 20 to 30 minutes, and this is kind of on the long scale if you're deploying any type of sizable payload. Oftentimes it'll be more like around 10 to 12 minutes. Power failures can lead to catastrophic loss of the vehicle if it's at any given altitude. But again, that is why you would have insurance for covering that type of thing.
How much does that weigh?
This vehicle, with its minimum payload of a high-resolution camera, weighs in at about 8 pounds. We have one that operates with a hyperspectral imager, and this is about an $80,000 camera, and it weighs in at about 12 pounds. And that vehicle flies for 20 minutes at that 12-pound payload limit.
Does your drone insurance cover the payload?
University of Hawaii's drone insurance does. Mine just insures my manufacture of that vehicle.
It's typically liability insurance. You can get an additional rider to cover loss of the actual equipment, including payload.
Exactly. Insurance will sell you any type of insurance, is the bottom line. So this is a case study that we did with the University of Hawaii, and we've been working with University of Hawaii for about 3 years now. They came to us quite early on through the recommendation of just another person in the field. It's kind of been a small community. It's starting to grow, but those of us who've been in it for a while kind of all know one another. The task there's this group down at the University of Hawaii SDAV lab, or the Spatial Data and Visualization Lab, essentially was a small group of experts in their field. They understood geology. They're geology scientists and researchers, a few GIS experts, and they really understood the value that remote sensing could bring to what they were doing. Every type of data, that you could sense from the air, and they could build that into a visualized environment. And on the budget that exists in most schools, I'm sure, this is about the most economical way to get data. So this was a project that we did last year. This was in Kona, Hawaii, at Pu'uhanoa Honau National Park Survey. I will refer to it as the Park Survey after that. But we flew this in 3 flights, primarily because the park was open at the time. In 2012, the National Park Service explicitly said that no drones are to be flown over a park for any reason. So this was actually the first FAA sanctioned flight over a national park since that ban went into effect. So that was kind of a exciting moment for me. I was actually the pilot in command on all of these flights, primarily because we were flying the payload for a portion of it, and I think they didn't quite feel confident to do that themselves. We flew it in 3 portions. This was the Coconut Grove, and then the inlet area here, and then this area. This is King Kamehameha's kingdom, or at least the remains of it. So we flew it in 3 15-minute flights, once over each one of those sections, and during that time, we did have people who were keeping traffic out of those areas while we flew over them. Most people were really excited about the idea. There were 1 or 2 people that were really not welcome to the idea of being restricted from walking around the park, but there are always those few bad apples. We flew at approximately 150 feet. The total coverage area was 34 acres. Out of those 34 acres, we took 575 images. And each one of those images were geotagged, so we knew the exact camera location of each one of those images. The image sensor that we used, or the camera, was a ILCE, or an interchangeable lens QX1. This is a Sony camera. It basically is about the highest quality camera relative to payload size for these types of applications now. Very low noise sensor, so creating the maps that are generated from this is sort of the same effect as the laser noise sampling. The lower noise image, the better the final image, or the better the final map. Our resolution on the ground for this was 1 centimeter, so that means that in our final map, a pixel on the ground measured 1 centimeter. So by that, you can understand that a pack of cigarettes would be easily visible. Something that was just 1 centimeter in size, would be a pixel. So you kind of get the idea of what you could see on the ground. We had 8 ground control points, and you can see those with the blue flags here. And so those were set out using an RTK GPS system. So that's a high accuracy GPS system. So we set each point as a visual target on the ground. This is incorrect, the mean accuracy. I had put this in as kind of a placeholder until I heard back from U of H. We were closer to 3 centimeters in the X and Y plane and about 5 centimeters in the Z plane. That would have been much better if we had set more targets, but we only had 2 days to complete all of the flights, and we were dealing with rain and people walking around. So rain in Hawaii, right? Every day at 4. So this is a digital elevation map that was generated from that flight. This is one of the products that from a photogrammetric model can be produced. So you can create an ortho photo. So an ortho photo is a full-size photo at the resolution that you captured. So for that map, the ortho photo is something like 38,000 pixels wide by 48,000 pixels tall. It's an incredibly large image. It would kind of cover up a lot of that wall surface there. You can generate digital surface models, which are basically a smooth texture that drapes the surface of the model that you covered. A digital elevation model, which will, this software, essentially, it understands what the ground surface is. You can basically describe that it take away all of the buildings and surface texture. This is sort of similar to some LiDAR techniques. It's not quite as accurate as LiDAR techniques because the depth filtering just isn't quite there the same way. But then it allows you to create a digital elevation model. You can create contours from that. So you can generate a lot of useful tools for larger topographic modeling. An interesting point that I wanted to describe here is that using these digital elevation models over large areas, you can often define perhaps previous constructions that have been covered by sediment or vegetation. A project that has just recently been done in central part of France was using a small LiDAR sensor, or relatively small. It's about a 2 kilogram or about 4.5 pounds of sensor, but it is a LiDAR sensor that they were able to identify under vegetation a hilltop fort that has been known about since about early 1800s, but has never been explored because of the vegetation overgrowth. They were able to do a microtopography of that hilltop fort and identify windows, entrances, ramparts, all sorts of distinguishing features about that fort. And it's really been the first time that it's been explored that way. And archaeologists have been kind of astounded at the level of detail that can be generated from a type of survey like that. Looking at methods for map data accuracy. This is similar to how Matt described the registration points that are used to stitch together certain parts of or the different blocks or chunks of a LiDAR mapped building. We use these to basically geo-rectify a large map. So what you're looking at here is the ortho photo at a down sampled rate as you're looking at the full ortho photo. As you zoom in, you can see that right here is one of the ground control points. You can see it a bit clearer here, and this is that ground control point. And if you zoom in further, you can see it pixelated across this marker that we use. Now, the center of this marker defines where a very precise GPS location has been measured. And so we put those GPS measurements into a spreadsheet. And then as we identify each of the features that are marked with an X and their corresponding GPS location, it essentially corrects all of the errors or corrects all of the area between those locations. So the more of those you have, you can think of it kind of like stretching out a canvas. The area in between is relatively tight and organized, but each one of the points where you have a defined measurement, each one of those points are very accurate. So the further the area in between those points, the less accuracy your overall model is going to have. So the idea is to have more GPS or ground control points for tighter precision over the model, and then also to have those ground control points be of the level of accuracy that you want in your overall or your finished model. The targets and these locations are tagged on the photos prior to creating the map. So then that's essentially that's the process for doing that. You find each one of the X's at the full resolution, you drop a pin in it, and then as you go through the photos, you'll see more and more of the photos with that same GPS or that ground control point with a pin located in it. For areas that are sensitive, you can essentially put the ground control points around the perimeter of that sensitive area, and it'll still apply some level of that accuracy to that area. There will be times when you either have no access to an area or for reasons of preservation, you cannot walk on that area at all. For those times, you can use camera location data to create some level of accuracy close to that of the ground control points. For this, you're basically defining the location, the exact location where each image is taken, and then the software uses that information to basically geo-rectify the map. The issue is currently between the refresh rate of your GPS location. So right now it's normally for most of these systems around 5 times a second. If your vehicle's moving at 5 meters a second, then that error can grow quite quickly. If you can't define the exact moment that the sensor is exposed. So the exact moment you take that image needs to correspond with a GPS location of your exact moment in space. So there is it takes quite a bit of work to build a system that can capture to that degree of accuracy. So it's a good idea to be able to use a bit of both of these systems or a bit of both of these methods to generate accuracy. RTK on the vehicle itself is becoming more widely available. It used to be a proprietary technology, and what RTK is, it uses 2 GPS beacons, one at a known location and one, in this case, on the vehicle itself, and an error correction between those 2 vehicles to take what is generally an error of about 1 meter to 2 meters for the location of a GPS beacon down to just a few centimeters. In the best instance, for some of these open source systems, you're looking at about 20 centimeters right now. but over a large map like this, that can still generate a very accurate model. Since no ground control points are even necessary for this method, basically you can use it on any type of site, whether it's accessible or inaccessible, or for reasons of site preservation. Where we are going to get in a relatively short period of time is that RTK GPS and image capture will be synchronized to the point where ground control points won't really even be necessary. Right now, they also act as a ground truth. So if you know this is the exact location on the ground, then using that in coordination with camera location data will start to generate a valid argument for the accuracy of maps created just with camera location data. So this is a project that was done for the regional open space district. It's Mount Umunhum in Santa Clara County. This was a decommissioned Air Force base. Here is a radar tower that was used to look for aircraft coming across from Russia during the Cold War. The open space district is now making this into a green space recreation. And what they needed from Sandus Civil Engineers was a planning phase study. And so Sandus had bought one of our systems and was an early adopter. They thought that this would be the perfect project. So I wanted to describe a couple of sort of the key points about this and what we found out, in discussing the project with them afterwards. For this example, it was especially useful because the site did have hazardous materials and unsafe conditions, as there were a number of partially demolished structures. Overall, the area that they had to map was largely inaccessible. And so it would be difficult to create the map that they were asked to do because of sort of the land conditions, whether it be sheer cliffs or just heavy vegetation. One thing I wanted to kind of go back to, the same situations existed here as with University of Hawaii, in as much as they were experts in their field, survey being the expertise here. They understood the technology advances that could really change the way that they were doing their work. And they generally understood the cost savings that were associated with that. And so we kind of walked this company specifically through a number of their first projects, and after that, it really kind of took off for them. And I think the survey industry is one of the most disrupted industries right now because of really just the technology that's come along. The survey industry has been largely valued for the knowledge base that was required to be able to generate a topographic map like this, and the complex mathematics and training and everything that was involved in translating world data into documented visual data. Now what we have is essentially a calculator that we've brought to the mathematicians. Anybody can really pick this up and generate relatively accurate map data without years of training. And so we have seen the legislature in different areas pass rules relative to this. Now, I've always been more about kind of trying to back the survey industry and provide the new tools that will help propel them, make them more productive. But it is definitely a disruptive technology, and we'll see kind of who picks that up and who kind of falls by the side. For this survey, it was 2 20-minute flights, one over the upper area here, and then another over the lower area. They flew at about the maximum altitude. It's 400 feet. They flew at approximately 387 feet above ground level. This covered about 75 acres, including a small area down here, the Guadalupe Creek Overlook, I think is what it was described. Over these two areas, we captured about 244 images. And one other correction here, the camera used was a Canon A2500. That was on one of the earlier versions that we created. Lower quality, higher noise, but still very good results. The ground sample distance, because of the altitude, was closer to 3 centimeters as opposed to the 1 centimeter. They did set 45 ground control points. It took them approximately 7 hours of that day to set the ground control points. You see another about 20 down on this side. The average accuracy for this model was 2 to 3 centimeters in the X and Y, or kind of longitude and latitude, and then 5 centimeters in the Z, or altitude measurement.
Can I interrupt you again?
Yes, please.
Go back to what starting to say that I was trying to understand the number of people doing this kind of work now, their background and lifestyle or whatever is changing. Is that what you're trying to say? I didn't quite follow.
Oh, I'm sorry. Yeah, I was basically saying that for the survey industry, this is a technology that essentially, it's, as we've heard, how AI will be disrupting technologies. Well, the first will probably be those that are largely concentrated on mathematical concepts. So the concepts of survey are largely mathematical, to create topographic maps from triangulated measurements. And so what we have now with either LiDAR data or photogrammetric data, which acts very much the same as LiDAR, except instead of measuring the time of a laser pulse from here to the wall to take that measurement, it does it through stereo vision, essentially. So through multiple images of that wall, I would be able to define not only features about that wall, but height data from that wall. Because I'm taking, that shelf, I can't tell how deep that shelf is because of where I'm looking at it. But if I took a picture of it from here and then a picture from your view, then I would have a much better idea of the depth of it. And so that's kind of how photogrammetric data works.
So your comment basically that things are in semi-turmoil and changing because of all the new abilities we are creating? Is that it?
Yes. I mean, that's what we found kind of working in the survey industry. Yeah. And to the point that Matt made, that perhaps, they're not really looking too much at LiDAR because surveyors aren't really surveying that building. They are definitely looking at drones because, and what you'll see in the next slide is pretty.
I guess it's like I'm the last one in the office who still does drawings with pencil.
Oh yeah, I love drawings with pencil.
On the computer, so.
And what is done in the office? Okay. Well, as you're aware, kind of the most fluent.
I'm good at doing it with pencil, everyone else can, the computers really are a wonderful thing, but there's only, I don't know, I just feel more comfortable doing it.
Yeah, it's sort of like trying to describe your favorite food in a foreign language. I mean, the best way you can do it is in your fluent language. So with a pencil, that's the best way to express an
Well, I
idea.
guess I'm sensing from you that it's this whole change in lots of creations like phones and things that are
Sure.
changing how you work as well. I mean, it's just
Absolutely.
for the
And
good, for the most part.
What's that?
For the good, for the most part.
It's for the good if you adopt it. It's like, a wave is disruption of the water. You can either kind of be pummeled by that wave, or you can get on it and really be empowered by that wave.
That's a good analogy.
Thank you.
Maybe I'll mention something about this site, because the challenges from a historic perspective is that, and I don't know if you went into the history of the site, more than saying it was an Air Force base, but there were 70+ structures on that site.
Okay.
Prior to them being demolished and everything, the open space district, but they were all considered potential historic resources. And if you were an architect or a surveyor going through each of these buildings one by one and looking at the conditions and doing condition assessments and everything, it would take you ages to do that. But if you were to fly over this with the drone twice for 2 20-minute flights, you'd at least have a good idea of what's there, what's possible to save, what kind of condition and integrity remains, and those kinds of
Are you
things.
saying someone decided they didn't want to deal with that, just tore them all down?
I think, well, I mean, that goes into a lot of politics, but the Mid-Peninsula Open Space District, naturally, because they're into open spaces, they think differently than preservationists would. And my hope as an advocate is that the open space districts would communicate more with preservationists and talk more about why certain structures at the site would be historic as interpreted pieces. But that's part of the reason why that cube is still there, because it was eventually determined historic and designated at the county level. So otherwise it possibly would be gone by now.
And I think, what was the quote on your email footer?
Oh, something about, I keep forgetting it. We don't want to be judged as a society that just creates things, but also as one that doesn't destroy things. And I think it was John Sawhill who said that. So it's a word that I like to live, or a quote that I like to live by, because it's easy enough to create something, but it's much more difficult of a job to think about how you can marry the creation of things with the preservation of them.
And for me, that translates into, if this is what it took to create a very high resolution 3D representation of this site, how easy is it for us just to take a quick snapshot like this before we destroy something? Again, coming up, doing arts and crafts, sort of renovations and restorations. And, when you were talking about Eichlers, on that Eichler that I worked on, there were several Eichlers on that block where you saw the Eichler inside somewhere behind like the new front, box that had been attached to it. And so it's very hard for us to really appreciate the historical significance of a thing until later, until that thing has been brought down to a rarity and we start to understand the subtleties about what made it so significant.
It's too bad they didn't hire you to take high resolution images of everything when it was not demolished.
Agreed. Yeah, absolutely.
Sorry, just your time check. It's 4:07.
Okay.
Sorry.
Yeah.
One more slide.
Great. Perfect.
So this is the cost comparison in the typical methods that Sandus would have used to do this same survey. So what we're looking at is the traditional survey is in the light blue. A manned aerial survey done with an airplane and a high resolution camera is in the dark blue. And then finally the unmanned aerial survey, which they did, is in the gold. So for the elapsed time, the number of days for the project to be completed, for the traditional survey, it would have taken about 21 days. This is the amount of time it would have taken for the survey engineers to go out and set about 10,000 points of reference. That equates to about 60 hours of labor on site. You know, this is the elapsed time including weekends. And then the actual cost would have been about $27,000. This is what was represented to us by the lead surveyor at Sandus. For the manned aerial survey, the time would be about 42 days. That would include basically contacting the aerial photography service, contracting with the photogrammetry service. We would then take those images and transpose them or translate them into models, and then getting the, I guess, the flight planning and all of that carried out. There would still have to be ground control points set out for that manned aerial survey to be accurate. And the cost of that, I think, was about $30,000 just for the manned aerial flight and the photogrammetry, and then they still had to build their documents and products. Sandus still had to build their documents and products from those deliverables. So that came out to about $35,000. For the unmanned aerial survey, you're looking at about 1.5 days. They went out in about 7 hours. They set those ground control points. In the next hour, they flew the 2 missions and then packed everything up. That's about 8 hours on site. And so then the 1.5 days, they basically took all that back to the office. They registered the control points on the photos, and then they set it to processing, which that took overnight. The next morning they came in and had the 3D model ready to go. From that, they could export digital elevation models or digital surface models, create contours, and generate the rest of their documents. And they basically estimated this cost about $4,500.
Do you have a detailed photo of what one of those maps looks like? Zoomed in pretty far?
Well, that's the thing, is given the size of it, I do have those ortho photos, but they're difficult. My expectation was that I would kind of be presenting from a queued up presentation, but you know, I could show you that at a later point in time. But yeah, it's typically down sampled in most of the ways that you have to view that. So if you view it, that's kind of what we see here. This is an actual representation of the ortho photo as you would see it on your computer. And then as you zoom in, it basically repixelates or depixelates to reveal the full resolution of the image.
Yeah. Okay.
Any final questions? Okay, great. Thank you, Sean.
Absolutely.
And thank you, everybody for attending, all the speakers, wonderful presentations today, and please do continue to attend our program. So please, a round of applause for all of our speakers.